Continue kind of this discussion of basically strain gauges and work a couple problems, and especially on this one, how you can kind of strategically put your strain gauges on your material and selectively kind of cancel out some components, whether that be axial tension, whether it be bending, temperature, et cetera, et cetera, et cetera, et cetera. So let's start off with, we know our fundamental expression. We know 4, 1 minus 2 minus 3 plus strain in 4, assuming our standard Wheatstone bridge configuration. Here, here, and here. So 1, 2, 3, 4. So now, all we have to do, or we're trying to kind of figure out here, is how do we kind of strategically place these to eliminate some properties. So we have a novel material in a uniaxial tensile test. I'm going to set up my system where this is 2, this is 1. So there is some stress in the 1-1 direction. We could even just kind of, actually, let's go ahead and always do our 3-dimensional coordinate system, just to kind of make our lives a little bit. So 1, 2, 3. So there is now stress in the 2-2 direction. So there is positive tension in the 2-2 direction. We need to have temperature compensation. But due to various constraints, we can't use dummy gauges. So we can only use 2 bridges in the standard Wheatstone bridge configuration, but there's only pure tension here. So let's look at this kind of material flat here. So we're pulling in this direction. So we need to have two strain gauges. So let's see what happens. So I have 2 strain gauges. Let's say I put my material 1 and 2, and they're on the top. So what's the strain in 1? Well, it's just going to be kind of, again, this strain due to the stress in the 2-2 direction. We can, again, rewrite this. So we know that the strain in 2-2 is equal to, let me get some room actually. Oops. So I know that the strain in 2-2 is equal to 1 over E times sigma 2-2 minus nu times sigma 1-1 plus sigma 3-3. We know that these are zeros, so it's just the strain again in this 2-2 direction. So we know that in 1, strain in 1 is just the strain in 2-2 direction. And it is going to elongate, so it's going to be positive. Is 2 going to be negative? No, it's going to be the same, right? So the strain in 2 is just going to be that same strain. Now, your material is always expanding due to temperature, so there's always this kind of temperature expansion here. So if we plug that in, would we compensate for temperature? Yes, but we would also cancel out these values, so that won't work. Now, what happens if I put that strain gauge on the bottom of my material? Will that strain be negative or positive? Well, it's still going to exist, right? Like it's still going to extend in that direction there. So we're facing the same exact problem, so that doesn't change our answer at all. What happens if we keep it on top or bottom? Again, doesn't really matter. What if we made this 4? So now my strain in 4 is the same value, right? Let me kind of rewrite this. It is strain in 4 is equal to, it's a strain in 2-2 plus strain in temperature, strain 2-2 plus strain in temperature. So now we would add that, right? So your E total, which is this value, your E total would just be 2 times E22 plus E2. So we're not getting rid of temperature. When we say temperature compensation, we need to get rid of the strain in temperature. So we're kind of stuck, right, at this point. Like it's not, nothing seems to be kind of working out for us. Like every time we subtract, we kill off all of our strain. But what happens, or what would happen if I instead, let me erase this. What happens if I align my strain gauge like this, in the 2 direction? What's happening now? Well, the material, let's look at the 2. As I pull here, what's happening to my wires? They're contracting, right? They're moving in, basically, in this example, if you kind of flip it, they're moving in the 1-1 direction. So the strain in 1-1, the 1-1 direction is just, again, 1 over E times sigma 1-1 minus nu times sigma 2-2 plus sigma 3-3. We know that this is 0, this is 0. So again, it's just the strain due to that 1 in the 1-1 direction minus your nu. So you can rewrite this again. So your strain in 1 is equal to minus nu sigma 22 over E. But we know previously that our strain in 22 is equal to just our sigma 22 over E. So you can rewrite this again, depending on what you're given, that the strain in write this. So our strain in the 2 strain gauge is equal to just the strain in 1 plus E sub t, or you could rewrite it as the strain in 2 is equal to minus the strain in 2 direction plus E sub t. And there you go. So that can be, help be consistent if you're trying to measure, and what we are, we're trying to measure the strain in that direction. So those are equivalent kind of values that you could calculate right there. So what happens when we plug this in? Now the temperatures kill each other out. So now I'm left with my E total, my strain total, is just going to be E22 times 1 minus nu. That's it. So I have accomplished my goal. I've gotten rid of, there's no more kind of temperature because those subtract that. Or actually, plus because that's a minus. That's it. That's all we've got. So that is how you would kind of compensate for your strain, basically the strain gauge there. Now, it also asks us to calculate the bridge constant. So the bridge constant is K equals A over B. So this is the total output, so total strain, versus the output in arm 1. So our gauge constant, or bridge constant, excuse me, is going to be my arm 1, which is just E sub 22 plus ET over, basically minus, the total is actually, excuse me, E22 times 1 plus nu. That would be your gauge constant right there. If you assume that the strain in temperature is small, you could again simplify this to just 1 over 1 plus nu. If you assume that this is small, which temperature usually is extremely small. Fantastic. Let's go down a little bit further and look at a more complex stress state. So I want to kind of figure out, this claims that the bridge constant is 4. Let's write out what is the strain in each of these kind of moments. So we're being stressed again in this 1, 2, 3. So we have a stress in the 2 direction. So I want to figure out what is the strain in 1, 4, and then again, we're bending basically like this way. We're bending like around, we're stretching that one. So in the 1, we have positive bending because we're on top, and we also have strain in the 2 direction. And what else do we have? Always temperature. 4 is going to be the exact same, right? 2. What about 2? The only thing that changed, we're going to be we're going to be compressing there. So minus E bending, still expanding in the 2 direction, and then also in temperature. And 3 is exactly the same. There we go. Add all those together. So I'm going to end up with my total. Epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. So you're going to see that we're going to end up with 4 EB. And because those subtract, these all get canceled, and these all get canceled as well. So 4 EB. So our gauge constant K is going to be equal to, again, what's in our first arm? EB plus E22 plus ET over 4 EB. That's it. Or bridge constant, excuse me, not the gauge constant. That's it. So again, think about how you can rearrange and kind of change your orientation of your strain gauge to kind of eliminate different components, and more importantly, see where is your strain gauge elongating, where is it being compressed, and how you can kind of play around with that to basically measure different types of strains in different directions. Yeah, so that's about it. Thanks. Let me know if you have any other questions, and yeah, see you all next time. Bye.